Good morning, ladies and gentlemen. Pleased to see you again after a long break. You kind of feel look relaxed. That's nice. So, what do we do today? It's a rather important topic. We will chat about what you actually see every day, every second your eyes are open. We will talk about radiation and matter, how matter would produce light. See how it produces radiation, despite many things. First of all, we want to understand in better terms what is the emission and absorption rate. Funny enough, it's a mass quantum mechanics, but it's anti-quantum mechanics. All these rates presume that we are in well-defined states. So in fact, it's an attempt to smuggle classical physics into pure quantum mechanical description. Okay, so for a while, we will discuss the situation. We will try to figure out why it is possible, why it has to be done, and how does it work, how to compute these rates. Then we're not there yet. We will talk about emission and absorption in very general terms, even don't specify into electromagnetic field. Just talking about general linear field. So the discussion is rather general. We were able to figure out pretty much about emission and absorption. And with that, we again make use of smuggled classical concepts. And again, we depart from precise quantum description. We will talk about master equations, very simple balance master equations. Matter emits something, it changes state with some probabilities. Photons appear, disappear, emitted and absorbed. That we will put into the scheme of master equation. Blackbody radiation, it's eventually the mere onset of quantum mechanics. That's how and why quantum mechanics has been introduced at all. So we cannot miss this topic. We will talk a little bit about Blackbody radiation. Good. After that, we can concentrate actually on matter and radiation, namely talking about atoms and electromagnetic field. To do this, we have to do a little bit piece of work. We have to figure out what's the interaction between matter and radiation. Once and forever, then you can just play till the end of your life. But well, we will look at this. Fine. All right. Then we encounter something which is in my transparencies, in my slides. You can upload, but practice shows that I don't have time to talk about this. But perhaps it's also consistent because these topics are kind of fancy, but very applied in comparison with all other things we have to learn in our course. What I really cannot skip are lasers, which really kind of best application, human-made application of emission absorption. So we shall reserve some time to talk about lasers in the end of this lecture. But if I really concentrate on these topics, I could easily make this lecture to last till next morning, Friday morning. Let's try to concentrate and make it. Fine, so let us start with this strange formula, which is called Fumi Goldenrod. Golden is because it's such measure so useful that Fermi called it golden. And you might think that Fermi was somebody who really invented this formula. That's not right. Well, we just talk very much at large about this formula. We applied it many times, but the formula itself was because Heisenberg, you remember this little bit crazy young guy, he invented it, but it's really Fermi who kind of understands its significance, or to book about this. It's called Fumi Goldenrod. What is that about? It is about transition rate. Transition rate. We have some system, for instance, and potential radioactive atom, which wants to decay. How to characterize the speed of decay? It's a probability that this atom makes it to decay per unit time. So it's really a literal translation of the word rate in Dutch language in physical contents. So it's very short rate, but in Dutch it's waarschijnlijkheid. Probability per unit time. Good. So what is this probability of unit time? First, we want to understand where we start and where we go with this decay, with this transition. We have an initial state, and we have a set of final states. Set is important. But let us first see what is the formula. Right? Okay, some factor 1 will do it, but h bar, it's just conversion between time units and energy units in many quantum mechanical applications, not important, and h bar is 1. Never mind, I will put it here explicitly. What do we have to here? Okay, first summation over all final states. That's natural. If we have kind of probabilities of different outcomes, the total probability can be just the sum of these probabilities. All right. So we have here, it's a squared of something which has dimension energy. And this is perturbation theory. We have some perturbation which provides us these conditions, right? And we take matrix element of this perturbation between initial state and final states, right? We square it. And then there's very funny expression, which might seem natural. What does it say? It's delta function, and delta function not zero only if any initial state is the same as energy of the final state. Energy conservation, it has to be valid, right? It could not really extract energy from anything which decays. Energy must be the same. So it looks like in the right place. Let's see about it. So there is some initial state. And let me put here the energy axis. Let me put here the spectrum of final states. It is zero. Perhaps I have too little of final states. Let me make it more. No, they don't match. Transition rate is zero. Good. Let me just take the whole spectrum. Let me move it a bit. And yes, it matches at some point. And the rate erupts, becomes infinity. Delta function is infinity if argument is zero. So there's something terribly wrong with this formula. That is because we do something terribly wrong. Something which eventually is not a part of regular long-term approach. So if we have two states, for instance, here and here, and forget about all other states, what will happen in quantum description? Okay, there will be two states, they will be a little bit hybridized, no, but still we have two states and no transitions at all. We will be excited state, ground state, and the system can be exactly ground or like superposition. This is what quantum mechanics says. This is not what we see, right? We see in our eyes absorption and emission of quanta, and we have to adjust quantum mechanics to real life to this situation. That's why this is so paradoxical. There is a full derivation of this formula. I guess it's in my book on this course. It's also in many books. It's kind of tricky, not easy to follow, but there is. Let me just mention that it is a little bit paradoxical, but this is because it has to be like this. So pay attention to this. To make this formula meaningful, you should make the spectrum of final states a continuous one. You cannot use discretized spectrum, otherwise you would have either zero or infinity, which would make no sense. So at some stage, we will have to replace this summation by integration over some continuous set of the states. In our case, most likely this integration would be something which you know. You would have to replace summation of a discrete K, meaning like wave vectors and photons, to integration over delta K. And then it's gonna be all right. Good, it's Fumi Golden rule, a really basic method when it comes to the rates. Okay, so it only makes sense if we deal with continuous spectrum of final states. right, any questions about you? Kind of not fascinated enough? All right, let me try to get further. Now I'm gonna be rather technical, and I consider a certain example, but still I want to be general. I don't want to give you any specification about the states of matter, which is A and B, whether there are atoms or molecules or anything, because it's valid for everything. So we have two states of matter, A and B, and at the moment, at least at this transparency, A is excited state. Fine. So I want to understand how this interaction with photons would occur. Good. So I have the states of electromagnetic field. We remember that all possible states are characterized by just a number of photons in each mode. Modes are labeled by discrete wave vector, and who remember what that is? Yes, polarization. Each takes two values for each wave vector. All right. So what is the general Hamiltonian we can write here? Here it is. That part only concerns matter. It has matrix elements in the space of matter. That part concerns only photons or any other field which we have to excite or absorb from. So here we encounter creation and annihilation apparatus of photons, and they come only once. So again, we need to create or annihilate only one photon per at once. That's fine. So let me use this Hamiltonian. Let me plug in into Fumi Goldenrod formula. And to simplify things, we will be looking at the process involving a certain Q vector here. Processes involving a certain photon. Why is it true? Because, well, we could just, the total probability is just summation over all possible processes of the kind, just summation over all possible Qs. Fine. Let us see what can we find here. What are the processes? There are basically two processes, emission and absorption. Let's see if I get it right, because I sometimes mix up excited state and the ground state. So A is excited, right? Then absorption. Initial state is B. There are some photons hanging around, and one of these photons gets absorbed, and it goes to A. That's final state. What's emission? Just other way around. And eventually other way around. Naively, I would expect the same rate. No, it shouldn't be true. Let us see in detail what it is. Emission, it's excitation. So we have one photon more, and it can only work if initially we are in excited state, we have some energy to put into environment, to photons. All right, let us see. Let me use Fumi Goldenrod formula, and to this end, I would like to compute these matrix elements which enter expressions for the right. Right, so how can I proceed? First of all, I can separate it into matrix elements which concern matter only. The separators M, they are connected to matter, and operators X which concern only photons. Fine. So those are just numbers, some numbers, matrix elements, which tell us how strong is the coupling between matter and this particular Q. Right, and this is what we have to look at, right? But we know what is this. It just comes from the definition of annihilation operator, right? It is square root of m. Right, we do the same for emission. What's the difference? We have to create one. Let us see. We create so plus here, and the answer is the same square root, but with n plus 1. Good. So we compare. We got matrix squares of matrix elements for emission and absorption. Absorption is proportional to the number of photons. It's natural. More photons we have, more chance to catch it and absorb. Emission is somehow fancy. So just several things we have to do. That's a partial rate to certain k. And it depends on number of photons and a given state with a given k, right? We have to sum up overall case. What we, for instance, assume, which is very handy, is that number of photons only depends on energy. But we know what is the energy. The energy is precisely the difference, energy difference between excited and ground state of the matter. So we can use it. And what we got? Absorption rate is proportional to a constant times average number of photons at this particular energy. And emission has n plus 1. It is so, on one hand it's trivial, from the other hand it's important. That's why I devoted the whole transparency to this near end. Absorption rate is proportional to the number of photons. Emission rate is n plus 1. What does it mean? If there are no photons around, we still have some emission, right? If there are more photons around, that might seem surprising, but they increase the chance of the emission. That's why, yeah, it's a little bit artificial separation of the terms. This is called spontaneous emission, and this is called stimulated emission. So it's supposed to be supposed to sound better for engineers. But it is. But of course, if you have a process, we cannot we cannot really say whether it's stimulated emission or spontaneous emission. Photons do not know anything about this. Fine, it's important. It will become important when we lace. But okay, it's something to recall for the moment. Spontaneous and stimulated emission, and how does it relate to absorption? All right. So we have the rates. We know how to depend on number of photons, and we can apply, as I promised, to describe the situation in detail. But you remember, just when we introduce these rates, we have already betrayed quantum mechanics, if I may say so. So, to proceed further, we need to use classical concepts. We have some states and some rates of transition between these states. One can call it stochastic description. In this case, each quantum mechanical state becomes a classical one and is characterized, the behavior of the system is characterized by probability to be in this state. Two master equations are handy for us. Master equations is something which has kind of simple significance. One doesn't have to be Einstein to write it. One has to be just a master. One has to master the situation, understand what's going on. One can kind of make it similar to bookkeeping. You just need to have accurate bookkeeping of different terms. All right, for a change, I switched now definitions of excited and ground state. Let's see if I did it correctly. So that's change of probability per unit time related to the state A, which is ground state. And what can happen, how this ground state can change? There can be absorption. Okay, so we find here absorption rate, and we need to be in the state A at this moment. So we have a factor which is probability to be in the state. Okay, so there are outgoing terms. We go out of the state A. There are incoming terms where initially we are in state B. And then there is a process. What kind of process is this? That must be emission. It counts as 10 plus 1. Fine. Good, we do it for A, we can also do it for B. Let us see then the change of probability to be in B. Is it due to what? B is a high state. So due to emission. And this is what comes from A is from absorption. Good, now we have all rates in the right places. Let me make a simple foolproof check. The sum of probabilities must be 1, right? The sum of two derivatives must be 0. Good. So these terms have to cancel. That cancels with this. This one cancels with this one. Very good. if you sum it up. Huh? Fine, that's master equation 1 for matter. We also can be interested in the specific mode. What is the distribution of photons in a specific mode? And what's the parameter for the specific mode? Just number of photons in this mode. So we have a similar equation. Let us see, we are in the state with n now. What are the processes to get the system from this state to any other state? Absorption and emission both works, right? What's the absorption rate? Oh, sorry, absorption. Probability to be in the state A times number of photons. Same here. There's also emission. Fine. That's how the probability is lost. Terms coming with minus sign. There are terms which come with plus sign. Right? So how they made? Initially we have n minus 1 or n plus 1. Corresponding probabilities come here. And then we have the rates. Correspondingly, let's see, it is from n1 minus 1, we go to n, so that must be emission, right? And that must be absorption. Fine. We've made these equations, we can investigate it further. And what I was going to do is to talk about some important case of Blackbody radiation. And that is not about quantum mechanics again, yet another deviation from quantum mechanics, but quantum mechanics is the heart of science, so it has to be connected by vessels to all other sciences. So it's about thermodynamics. About thermodynamic equilibrium. So matter is in thermodynamic equilibrium, and that means the following: these probabilities to be an A, B are not arbitrary. They are related to the energies of the states and temperature. So we know already answer for the probabilities, right? But it is also assumed that photons are in thermodynamic equilibrium. So what does it mean? The ratio of two probabilities is the same as the ratio of two rates. That works for two states. Huh? So A, B, emission, absorption, the ratio of probabilities, just the ratio of the rates. Fine. And both in quantum state, both in the state of thermodynamic equilibrium must be like this. From the other hand, the energy conservation implies that the energy difference just the same as the energy of the photon. which are expressed in terms of frequency. All right. So that's what I get from thermodynamic equilibrium. Now let me recall this the beginning of this lecture. What do we get from quantum mechanical calculation with golden rule formula? That rate is proportional to n plus 1, and this is proportional to n, average number of photons at given energy. So from that, we immediately conclude that in the state of thermodynamic equilibrium, the number of photons must satisfy Bose distribution. Which should not come as a big news. You know that photons are photons, so they should obey all the general distribution. And now we see how does it come as a balance of two radiation processes, emission and absorption. Fine. We can also figure out a different quantity. So far we look at average number of photons. We could look at more details. We could figure out from master equation 2 what are these probabilities to have n photons. All right, we can solve this equation, a stationary case, and then again the ratio of two probabilities would be just the ratio of for matter, what we have for matter, probability ratio of two states of matter. That is given by thermodynamics. So we find that probability is proportional to Boltzmann factor, and h omega is in fact energy of each one. So we make everything consistent. Dynamics of a balance of emission absorption processes reproduces what we know about thermodynamic equilibrium. Fine, let me just understand it in a more spectacular situation where thermodynamic equilibrium is present and absent. First of all, let us understand, if you read about, usually it's kind of in the introductory course of physics, this Blackbody stuff. Let us recall what does it mean. We take a sphere, and inside sphere, we really have something black, which absorbs photons. Each absorption is emission, right? We see that. So its final temperature, so some number of photons which fly within this black body. So we make it an opening, and here we break thermodynamic equilibrium of gas. Now the photons can go out, can leave this system, and that's gonna be black body radiation. Absorption and emission of photons which are completely in thermodynamic equilibrium. You have to break this equilibrium in order to absorb these photons, but that's kind of a least invasive way of breaking it. Fine. So, what else to do? Let us compute the number of flux which we get from this opening. First of all, let's make it wider. So we can, at the moment, we assume that in our scale, the opening is sufficiently wide, and the flux is proportional to the area. So I normalize it to the area. So what do we have? Some photons on the left, and they go to the right. No photons which go from the left to the right. Okay? Because there are no photons outside the sphere. To distinguish that, we need this vector Heaviside function, which sorts out only photons which come from the left. Yeah. Well, if we would add also photons coming from here, we would get 0 for the flux. Huh? We don't. So now we can have actually flux velocity and energy of the photons, number of photons, correspondence to thermal equilibrium, and we have to sum up over all photons, and we replace summation by fine. So what do we got? I didn't make all integrations. I registered the integration over frequency. And right, the answer which we got was eventually first obtained by Planck. It contains Bose distribution function, and it contains a factor proportional to frequency. Photons with more energies contribute more for the flux, but there are no photons above certain energy. So if I plot on this, I got red curve. That's more or less spectrum of sound spectrum of Blackbody irradiation. Little photons at small energies, at peak, at energy of the order of temperature, and nothing there. But nothing is because of very ingenious, I don't want to call it dirty, so I call it ingenious modification of Planck, who just put by hands without knowing quantum mechanics, Planck constant to this question, just to cut this tail. If Planck constant is 0, the number of photons, and that is kind of clear from classical physics, is kBt divided by, let's see, h per omega. And right, so what you have to integrate, it just this and that diverges. That would be classical prediction to the destiny of our world, which is best expressed by shining gas. Right, so why this one? We see that the rate diverges at high frequencies. So anything which has any hidden side, like a star, should lose this energy just instantly and got into light and subsequently. Quantum mechanics saves our lives from this unfortunate outcome. All right, let's have 7 minutes break to kind of get used to the ideas that we see in life. We have figured out about Blackbody radiation. So it was half of the lecture about very general properties of emission absorption. Let me specify. Let me talk about electromagnetic field and say electrons, charged particles. Right, gauge trick, which enables us to derive interaction between matter and radiation. First of all, Schrödinger equation for a charged particle. I just skip the potential at the moment. And I can transform wave function, just do something mathematical, in the following way. I can give it as a phase vector. I give it a phase vector, so I got Schrödinger equation for new wave function. There are extra terms coming from this derivative and that derivative inside. And the trick is to identify this transformation with another transform, which we know about, which is completely classical, gauge transformation of electromagnetic fields. Upon this gauge transformations, we discuss any gradient which you can add to vector potential, any time derivative which you can get, which you can add, subtract from electrostatic potential, just doesn't change anything. It just another choice of gauge. That gives us an idea that if you would like to take electromagnetic fields in Schrödinger equation, we just have to do a substitution, which is again a bit creative because it's wrong. So what is wrong? We have replaced insignificant change of gauge with what is changed, with a vector potential and scalar potential. But in this way, we make sure that the total equation is invariant and the simultaneous change of phase of wave function and gauge change of the vector and scalar potentials. What is the outcome? Outcome is that we have this equation. So we have a vector and scalar potentials can only enter Schrödinger equation in this way. The reason for this is gauge invariance. Yes. Why is it wrong? Why it is wrong? Why would it be? Oh, why it is wrong? Because if you look at this equation, it's not equal. It is not like this, and it is not like this. It can be changed by this amount, but it doesn't have to be equal. Right. So, simple way to talk about this, it's about derivative elongation. So each derivative acquires an extra term, potential in the case of time derivative, or vector potential in case of gradient. Good. So now we know how to put electromagnetic fields into Schrödinger equation. So let us second quantize this field. It should be so difficult. We can quantize any linear field. So let's have Hamiltonian and promote it all to operators. Okay. Those are operators of electrons. Creation and relation. Here in A, we have electromagnetic field. Then there is a kind of a step which is not very logical by itself, but logical for humans. We separate electromagnetic field into scalar potential to describe the effect of instant interaction in atoms. Atom is tied to proton because of this interaction, right? And that we regard as a matter, although it's due to potential. And we keep only A as a field. Okay, so from common logics, it's kind of not very logical because we treat electrostatic potential and vector potential differently. But for us, we live in non-relativistic world. It's quite a natural approximation. Good. So with this, all these terms, they eventually come to matter. And just describe interaction, Coulomb interaction in atoms. We have Hamiltonian for irradiation, which we have derived in the last lecture. It's been a long time ago, but it's just a summation over all energies of all photons with creation and annihilation operators, right? And we have interaction term. That doesn't look like comprehensive or easy to memorize. Let me operate it a bit. Let me note that, okay, what we have here is eventually gradient. The gradient is an operator of momentum, and if you divide it by mass, you get velocity, and if you get velocity, you get the current flow. So let me just replace it by operator of current flow. And that is easy to remember, right? Let me understand that we have precisely the structure we had in the beginning of this lecture. It is a sum. In our case, it's sum over coordinates. And this operator is all about matter, about electric currents which are produced by moving electrons. And that operator is solely about radiation and its linear composition of creation and annihilation operators. Fine. So I put different definitions of operator of current density. Second quantization. Here without second quantization, so just contribution of individual particles. I didn't present it as a quantum field. Also good message of this formula. What I wrote below, it's about classical. But if I would like to look at relativistic electrons, the formula stays the same. Very convenient. Good. Simple, convenient formula for interaction between matter and radiation that completes this piece. Good. So how to proceed with the transitions? We just grab this formula, put it into Fumi Goldenrod, and compute the rates. Fine. So we go to atoms. And perhaps I really want to energize your first year physics or perhaps even school physics. So let me formulate it as a paradox. What we are going to compute is the emission rate by atoms. So atoms are in some certain states. They decay, they emit photons. Right? The energies of these photons should match energy differences of atomic levels. Levels in atoms are discrete. That was yet another discovery which has led to formulation of quantum mechanics. So atomic spectrum should look like this. A sequence of discrete lines. Who's seen these lines in physical practicum over here? Who did physical practicum over here? That matches. How could you be a whatever, even engineer, not mention a physicist, without looking at spectral lines? Good. So next time you'll go to lab to look at spectral lines. But whatever. That's so fascinating. Anyway, look at the video, what can I say? Again, what I wanted to say is that if you have atoms, you expect discrete emission lines of different color, fine, corresponding to different transitions between atoms got excited and they emit quanta in these discrete lines. Okay, statement A. Statement B, the sun consists of atoms. Okay? Now let us look at the spectrum of the sun. It's continuous, it's spectrum of Blackbody radiation very close to it. So, you can explain me why.
The radiation of the sun is not being caused by this emission by some other process.
There are two statements which seem to be contradictory, right? First statement, sun consists of atoms. I could agree with this. Or another contribution that atoms provide you discrete lines. Both statements are correct, but the conclusion seems to be wrong. What is wrong with this? What is the catch?
Because every atom in a different line. So
The atom is supposed to be the same, and some consists of, if I'm not mistaken, 70% of hydrogen and 30% of helium, something like that. And all hydrogen and helium atoms are the same. Moreover, let me make it more fascinating. That's eventually, if you look carefully at the spectrum, which perhaps gives you a clue. If you look carefully at the spectrum, you see black lines, which correspond to emission spectrum of atoms. So how does it feel? Somebody talked to you about this in your first year at school?
the solar spectrum is just Blackbody spectrum.
It is a Blackbody spectrum, that's right.
Emission spectrum. These are two different things.
But it doesn't, it is still inconsistent, right? If some consists of atoms, okay, it could be some distribution of intensity in the spectrum rise corresponding to some temperature. But it doesn't say anything about continuity.
If you look in your spectroscope at like some gas, like a frail gas next to the sun, then you can see the emission spectrum. But not if you look directly at it.
Right, and why is it?
You said the sun consists of atoms, but these atoms are constantly moving around. They are at very high temperature, so they're also like vibrational modes being activated, like it's a big mess.
Yeah, okay, it goes to good direction. And because let me just accelerate. The isolated, these lines correspond to emission of isolated atoms. Atoms which do not know about each other. Right? If you have two atoms, energy levels are really combined. If you add third level atoms, there will be yet another structure in atoms in the spectrum. So the sun consists of rather dense plasma of atoms. That's why the spectrum of excitations is pretty much continuous. That's why it gives you continuous spectrum of radiation. And now you're almost there to explain absorption lines.
As far as I know, absorption lines you can see if you have some gas, a frail gas of your atom you're interested in, and you put this behind a bright, in front of a bright light source.
Yeah, so if you have a very hot sun, which is surrounded by much more dilute gas of the same atoms. It's called the gas, and it absorbs something which comes from sun. That's why we see, well, instead of bright lines, we eventually don't see anything at this position. No light, because sunlight is absorbed at this frequency by, I don't remember how it's called, exosphere of sun. Cold gas around, the gas around the sun. Okay, we know enough. So that is true, and we can compute the intensities of spectral lines in this situation. Right. Again, we do it as follows. We concentrate on spontaneous emission, so there are no photons around. Transition rate is obtained by squared of the transition matrix element and two states. Let us take S state of hydrogen atom and pi state. Transition between those. So atoms are unusually comprehensive. If I were a creator and if I wanted to give humans some tool set like Lego things to understand quantum mechanics, I could not make anything better than atoms. You really can't calculate everything about atoms with mathematics of, I don't know, 19th century to every detail. One can compute the spectrum of the atoms precisely, one can know what are these energies. All right, so what is about initial and final states? Initial state, excited state, and no photons in any state, and then Fk, sorry, final state with index k, it means that a photon with momentum k has been emitted. And we sum up, and I have already replaced summation by integration. I told you that it's necessary to have sensible answers from Fumi Goldenrod. We assume continuous spectrum of photons. Fine. And what can I say about it? It's rather obvious thing. The energy of a photon must match the energy difference between A and B. Fine. It's an important approximation, yet another simplification which an app enables us to play with mega blocks easily. It turns out that the scale separation at atomic scale, and this is called dipole approximation. First of all, let me talk about how does it simplify the formulas. We have current and vector potential, and we can neglect coordinate dependence of vector potential. And if atom is in position 0, we can just take this vector potential as a position 0. Why is it so? There is a difference of scales. Vector potential changes at the scale of wavelength, which is velocity divided by frequency, and for visible light, like 500 nanometers. And atoms are too small, it's only 1 angstrom. So there's a gigantic difference of scales between photon wavelengths and atomic size. Good, so we can use it. So we could just take for a formula which doesn't contain R dependence. Let's see. Here there are creation and annihilation operators, polarization vectors. Not to forget about this. Right. Now we're going to play a bit with matrix elements. So this is current. It's a current. In other way, it's velocity. From the other hand, velocity is a coordinate, is a dot. And by Heisenberg formula, it's a commutator of Hamiltonian with a coordinate. But if we apply Hamiltonians to the states of certain energies, the state A and B, we just get energy difference. So we can express the matrix element of momentum or the current in terms of matrix element of coordinate. And this is what is called dipole, electric dipole. That's why it is all called dipole approximation. So what we get? We have estimation of this matrix element, which contains this dipole element, so atomic size comes here. All right, and that comes from ugly square root I've mentioned in course of quantizing electromagnetic field or other fields. It's a coefficient in field operator. A is a field, it's presented as a field operator, it's linear superposition of creation and annihilation operators. Fine. So that gives us a rate in a certain direction. Let's see, how do I write it? At the moment, I have no chance but write rate into intervals. Not the whole total rate, but into interval, and this interval is an interval of solid angle. All right, so there's a sphere, all directional photons, and yeah, if I look at a certain direction, I would integrate over element of solid angle at the sphere, right? So that's what I got from Fumi Golden rule formula. I need to integrate it over three-dimensional K. 2 dimensions go to solid angle. 1 dimension stays in delta function. So 3-dimensional K I present as an integral over modulus Q and solid angle. And now I can integrate over Q, over modulus Q. And that, happily enough, cancels this delta function. We don't have senseless things already. Integrate it up, we have a well-behaved expression. So here we are. As a result, we computed the rate per solid angle. It's nice to keep in mind that it still depends on polarization and on the direction of this vector. Fine. You still need this matrix element, and you still need to integrate over angles. Let's integrate over angles first, because it's a kind of valid for any matrix element we can find. Right, so let me figure out. We just take this matrix element as a certain vector, which actually shows a vector of dipole moment. Huh? Right. Guess it's gonna be homework very close to this. But irrespective of homework, let me see what we can do. We have two vectors. Vector coming from atom R. We have also vector of photon propagation. And now we have some freedom to lose freedom of polarization choice. Let us choose two vectors of polarization in such a way that one is perpendicular to both R and Q vectors. Two vectors cross and polarization is in this way. And another vector is perpendicular. Fine. So with this, we can figure out what is the distribution of radiation as a function of direction of emission. Strange enough, but well, it is strange. Very good. Thank you. So even without knowing the intensity of this dipole moment, we can figure out intensity diagram. So the atom is in fact a small antenna. Let us see. What else can we say about atoms? We can compute overall rate. Still difficult formula. I simplified by introducing something which we have shortly discussed, fine structure constant. Very small number, about 10 to the minus 2, which shows that electromagnetic interaction not that important for atoms. Let me see, what do I have here? Yeah, perhaps let me talk about this estimation. So let us try to understand what we have computed, although we haven't computed it yet, but then the rest is just taking atomic wave functions, making these elements. We can estimate it without computing. What do we have? Let us make the ratio of the rate to the energy of frequency of the photon emitted. The idea is that we have kind of some oscillator of this frequency and that emits, right? So it's a quality factor of atom. In other words, it's how many cycles an atom would do in excited state. How long will it live in excited state? Right. So what we have from this estimations, dimensions factor, and it has one fundamentally small factor. There is another factor, which is, remember what I told you about dipole approximation. It's based on two difference in scales between atomic size and electromagnetic wavelengths, right? So we have this ratio here. So there's another small factor because of that. And if you express this factor in terms of alpha, it gives you another squared of alpha. So the rate is proportional to alpha. This dimensions ratio is proportional to alpha to the power 3, 1 millionth. That is quantifies how slow are decay processes in excited states of atoms. All right. So 10 to the minus 15 would be energy, would be inverse frequency, and 10 to the minus 9 would be typical decay time. A factor of million difference. Right, let me skip all that which is specific for atoms. Let me skip Cherenkov radiation. It's all nice and related to nuclear department, reactor. But I would like to talk about lasers. So that's a picture of laser. Who did practicum with lasers? Well, she did practicum with lasers. She didn't see spectral lines. Fine. More indication. So then those who did the practicum, you see here the light of two colors in this picture. What is the laser light? Which color? Did you really do practicum? Good. Recall sci-fi films. How laser light would look like. Yeah, something like straight beams. So straight beams are green. So that must be green, laser light. And you see for this realization of laser, which is helium light laser, it's not the whole light, it's not main light. So what do we have to do in order to make it lazy? First of all, it is, I really hate this cartoon, but I guess I have to talk about this. First of all, the laser is based on stimulated emission. Right? So for laser, we have some atoms into excited state. They decay in light. And it turns if we have many atoms to excited state, we can also accumulate quite some photons. And these photons will enhance the emission, will lead to the fact that these atoms decay faster. Ooh. Did it help, this picture? Me neither, but somehow everybody uses it. Let's go step by step. Let us, well, at least we have understood from this cartoon that we need to have some atoms in excited state. And we want to keep them, otherwise they will all decay, and it will be like shining death. And we have to make use of this stimulated emission. And if all photons in the laser would be gone, we won't get it. We won't have it. We have to keep some photons directly in the laser. Right? There are technical ways for this, mirrors or cavity. Again, who did practical on lasers? How did you keep photons? Usually it's like biological means perhaps it is just a system of spherical, almost non-transparent mirrors. So there are two mirrors at the end of this laser, here and here. And a photon has to bounce many, many times before this mirrors, and say it will leave this system of mirrors with a probability of 1%. That's what we have here in the beam. Right, so it may be a way. Let me look at the processes which go to in the laser, and here are, okay, I have at least Yeah, lots of different color. So how this helium neon thing works? It works on electric discharge. There's a mixture of gases, and it is excited by electric discharge, right? And that discharge, it's not random combination of gases. What they used to do with discharge is to energize helium atoms, and due to the collisions, helium atoms go to precisely to a state, and that matches to a certain excited state of helium atom. This mixture of gases makes such that these two states are of the same energy, so one can have easy energy change from helium to neon. And neon atoms, they decay. And mostly, they decay to 3-pi states, and that gives us lots of orange light. But there is also a probability of decay into the mode which is confined by 2 mirrors, which is a green one. Decay to the Lazen mode. Decay to all modes, and to this given one, can be a factor of 10 to the 20 bigger. But here, photons can be accumulated. So at some stage, the decay to a single mode can become a significant portion of the total decay. Okay, let's put it into equations. It is an equation on number of excited atoms. So there's income term. We always have a discharge which excites atoms. There is non-stimulated decay. So atom just got unexcited. And there is a decay into Lazen mode. All right. Then let's look at average number of photons in the Lazen mode. Here we have this stimulated emission, n plus 1. And we also have what we actually have to have. We have some light coming out of laser, right? So we have emission from the laser, which defines this quality factor of the mode. How many bounces it should do before a photon gets out. Good, 2 equations. One could also write, say, a second equation, which I would like to apply soon, but already without details. One can also get photon distribution in the laser in the same way. But first look at these 2 equations. One can solve it, so it's how can I say, competition between gain and saturation. If I plot emission from the laser, it looks like this. It's proportional to number of the atoms, but if decay into Lazen mode is too big, it also tries to diminish the number of excited atoms. So as a function of number of photons, the emission should actually saturate it will be like a curve like this. And it has to be equilibrium between emission and the loss of photons in the laser, which is proportional to this factor. Right? And the solution to this equation. What we see, it is a solution of this saturated line with different straight lines which correspond to different quality factor. So if quality factor is bad, we never have a laser. It means very steep line. If you make quality better and better, the line leans, and there is some intersection here. The equilibrium number of photons in the laser. Good. This is called laser in saturated regime. So emission is almost saturated. And again, just for fun, I would like to compute the probability in the saturated regime. Don't want to go to many technical details. Let me just show you the answer. Number of photons in laser modes can be really very big, like 10 to the 20. No, that would be average number for this distribution. There is a spread of this distribution around this quantity. It's because processes of emission and absorptions are stochastic. So there must be some fluctuations. This spread is square root of number of photons. Although it grows with number of photons, the relative ratio of spread and position is still small. Very well defined peak. Does it explain lasing? Let us see. It means that it fluctuates from state to state. So if we put the laser into motion, it's supposed to fluctuate a bit in intensity of the light, corresponding to transition between all these states. Those who did laser practical. Okay, it did. You don't notice, but it didn't fluctuate at this state. Yes. Good. That makes it a good motivation for the next topic of next lecture. Thank you for your attention for today. So, Zoom participants, thank you for your attention.